Good evening, sir.
I welcome to this session for the NPTEL course IC engines and gas turbines. This is our session 8. Right? In this session, we will be discussing mostly about performance analysis of Breton cycle. Right? So in Breton cycle, we have studied about ideal Breton cycle, the real Breton cycle, and some terms, for example, pressure ratio, temperature ratio, and some modifications in the simple Breton cycle, for example, intercooler, heat exchanger, and reheating. Right? So we'll try to solve some problems. Okay, so let's start. So starting with question number 1, it says that in a simple Breton cycle, where is the combustion chamber located? So this is very simple question, right? You know where is the combustion chamber. You know what are the various components and and the order of components, right? So first of all, there is a compressor. There is a compressor. So from compressor, we get compressed air, right? So in compressor, we send air. That inlet air can be at atmospheric conditions, 1 atm and room temperature. And that air is compressed in the compressor. And this compression process can be considered to be isentropic in the case of ideal Breton cycle. But in real Breton cycle, there can be some irreversibilities. Okay. So this compressed air, in this compressed air, some fuel is injected. Okay. Some fuel is injected. And since this air is very hot, this fuel will get ignited. If it is not ignited, then we are using a spark plug. But anyhow, we are burning some fuel, right? So basically, we are adding some heat, right? So this is a heat addition process. So in a ideal Breton cycle, this will be a heat addition process at constant pressure, right? So basically, we are adding heat. So there is a heat addition process. Okay, so heat is added where? In the combustion chamber. So this is our combustion chamber. So after constant pressure heat addition, what we get is our combustion products at very, very high pressure and temperature, right? So this high pressure and temperature gases are used for running a turbine. Okay, so these are used for running a turbine. From the turbine, we get the work output. We get the work output. And this gases which are coming out from the turbine, they can be thrown into the environment if it is an open cycle, or it can be recirculated to the compressor if it is a closed loop cycle. Okay, but before sending to the compressor, this need to be intercooled, right? Not intercooled, or maybe I should say pre-cooled, right? Here it is cooling process. So heat rejection, you out, then it can be recirculated to compressor. But in most of the cases, it is open cycle, right? Because you are adding some fuel and that fuel is getting burned. So there are some combustion products, right? So they are inert gases. So you cannot recirculate the whole mixture, right? So you need fresh air, correct? It is similar to our IC engines. So in IC engines, in every cycle we are getting fresh air. Just for ideal cycle, we are making this type of diagrams, okay? But in actual diagram, in actual case, it is a open cycle, okay? In ideal case, we are considering only air as the working fluid. But here in the real case, you can see that we are adding some fuel. But anyways, so question was asking where is the combustion chamber located? So you can easily answer that combustion chamber is just before turbine and just after compressor, right? Right. So combustion chamber is before turbine and after compressor. So option A says before compressor, this is not correct. After turbine, this is also not correct. Between the turbine and nozzle, this is also not correct. And option D says between the compressor and turbine, this is the correct option, right? So this is the simple Breton cycle. Okay. If I write the processes, in ideal case, I am writing, okay, in ideal case, in compressor, the process is isentropic compression. In combustion chamber, this is constant pressure heat addition. Constant pressure heat addition. And in turbine is again isentropic expansion. And there is a heat rejection at constant pressure. Okay. So what is happening is in each step in compressor, we are providing some work to run the compressor. In the combustion chamber, we are providing some heat. Okay. Basically, we are providing some fuel. In turbine, we are getting work output, and in heat rejection process, of course, is Q out. Okay. So these are the processes. Okay. Moving to question number 2. Which statement is correct regarding the thermal efficiency of the Breton cycle for a given gas? It increases with an increase in pressure ratio. It decreases with increase in pressure ratio. It remains constant with altering the pressure ratio, or it first increases and then decreases with the increasing pressure ratio. So as we discussed that there are 4 steps, right? On a TS diagram, if I make, then first step was isentropic compression. So 1 to 2, this is isentropic compression. Then 2 to 3, it was heat addition, right? Heat addition. Then 3 to 4, it was a turbine. So we are getting work output. And 4 to 1, or it can be just left open. Okay. So at point A, let us say temperature is T1, or this is the minimum temperature in the whole cycle. At temperature 2, this is some temperature T2 and pressure P2. Okay. And 2 to 3 and 4 to 1, these are constant pressure lines, right? These are constant pressure lines. These are constant pressure lines. So here P is equal to P2 is equal to P3, and 4 to 1, again, this is a constant pressure line. So P4 is equal to P1. Okay. So this ratio of P3 by P4 or P2 by P1, this is called pressure ratio. Okay. And you can also define temperature ratio that can be defined as maximum temperature that is at point T3 and minimum temperature that is at point T1. So in the lectures, we have discussed the thermal efficiency of the Brayton cycle, right? In terms of pressure ratio. So what is the formula? Do you remember the formula?
Yes, sir. 1 minus 1 by RP power gamma minus 1 by gamma.
What is that? 1 minus
1 by RP power gamma minus 1 by gamma.
is this right?
Yes, sir.
Okay. So if it is correct, then you can tell what how this efficiency will be affected if you change the RP pressure ratio. Will it increase or decrease?
Increases, sir. RP increases, efficiency
RP,
also increases.
right. RP increases when you increase this RP, then neta will be increased, right? So if you try to make a plot of efficiency versus RP, then you will get these type of curves, right? Right. So neta increases if you increase the efficiency. Sorry, pressure ratio. Okay.
Okay, sir.
The question number 3. The main purpose of using heat exchanger arrangement in a gas turbine power plant is to. Again, we have 4 options. Increase the net work output. Option B says to improve the pressure ratio. Part C says to improve the thermal efficiency or to reduce the compressor work input. So there are few terms: heat exchanger and net work output and compressor work input, thermal efficiency, pressure ratio. Okay, so pressure ratio you already know. Thermal efficiency you already know. Compressor is, compressor work input is the work that you are providing to the compressor, and net work output is whatever you are getting from the turbine minus whatever you are providing to the compressor. That is the net work output. So why we are using heat exchanger? So as we discussed in the previous examples, that the gases which are coming out from the turbine, that mostly we are throwing into the environment, right? And these exhaust gases, they are still very hot, okay, and they are having quite high enthalpy. So instead of throwing those hot gases directly into the environment, you can utilize the heat of those hot gases, right? So there was one process of heat addition, right? This is not parallelogram, okay? This is the TS diagram of Breton cycle. So whatever gases are there at point 4, they are having some enthalpy, right? Quite high amount of enthalpy. And 2 to 3 is the heat addition process, right? 2 to 3 is a heat addition process. So if the temperature of the gases at point 2 is lower than the temperature at point 4, so what you can do, you can preheat those gases. Okay, the gases which are coming out from the compressor, you can preheat those gases before sending those gases into the combustion chamber. So what will happen? You will utilize the enthalpy or the heat energy of the exhaust gases, right? So the gases which are coming out from the turbine, okay, so the gases which are coming out from the turbine, these gases are quite hot, right? So these gases are hot, and whatever you are sending in the combustion chamber. So why we are sending these gases into combustion chamber? So we can add some heat. Okay, and some heat is available at the exit of turbine. So instead of wasting that heat, we can utilize that heat. Okay, so we can uh, make a arrangement of heat exchanger between this point and the exit of turbine. Okay, so if we can exchange the heat between these 2 points, okay, between these 2 points, right? So what will happen? We will be able to utilize some part of the energy of the exhaust gases. Okay, so this is what is meant by using a heat exchanger. Okay, to increase the net work output. So will the heat exchanger affect the net work output? So what is net work output? Net work output is turbine output, work output of the turbine minus work input to the compressor. So if you are using a heat exchanger, are you disturbing anything related to compressor? Answer is no. Are we disturbing anything related to turbine? Answer is no. Turbine will work as it is. Okay, the compressor it will also work as it is. Okay, we are not disturbing compressor or turbine. Okay, so the net work output we are not disturbing anything. Only thing that we are disturbing is we are utilizing the heat of the exhaust gases to preheat the gases which are coming out from the turbine, so that the amount of heat that is required to be added in the combustion chamber, that will be reduced. Okay, so net work output is not disturbed, only the amount of net heat input is reduced. Okay, so whatever fuel we are using earlier, the amount of fuel will be reduced. Okay, so we will be able to save some fuel. Okay, so only we are reducing the amount of fuel required. Okay, and the efficiency is basically what? The net work output divided by total heat input, right? So you are reducing this heat input, but you are not disturbing this net work output. We are reducing this Qn. So efficiency will be increased, right? So heat exchanger will basically increase the efficiency. Improving the pressure ratio, no, we are not doing anything with the pressure ratio here. So we are increasing the thermal efficiency. And fourth part is reducing the compressor work and input. Again, we are not disturbing the compressor and we are not disturbing the turbine. Okay. So now question is, up to what temperature we can preheat these gases? Up to what temperature we can preheat the gases which are coming out from the compressor? These are horizontal lines. Okay. T2 and this is T4. So gases which we are which are coming out from the compressor, at max these gases can be heated up to T4, right? The temperature T2, it is less than T4. So if you use a heat exchanger to preheat these gases, then the temperature of gases which are coming out from the compressor, that will increase, right? But this temperature you cannot make more than T4, right? If a compressor has highest effectiveness, in that case, temperature at this point, let us say it is T5, then up to T4 you can heat it, right? So T5 can be less than or equal to T4, but it cannot be more than T4. Okay. So the amount of heat that you will be providing in case of heat exchanger, that will be H3 minus H5. That will be H3 minus H5 when you are using heat exchanger. And earlier it was H3 minus H2. This was without heat exchanger, right? This was without heat exchanger. So you have reduced the amount of heat input. In other words, we have improved the thermal efficiency. Okay. Sometimes this is also called regeneration. This is also called regeneration. Okay. So if it is clear, then we can move to the question number 4. Question number 4 says, in the Breton cycle, where is the intercooler typically installed? So in previous question, it was heat exchanger. Now it is intercooler. So in previous examples, we have discussed that higher pressure ratio provides higher efficiency. So if you want to increase the efficiency, you want to increase the pressure ratio. So increasing the pressure ratio means you are increasing the amount of compression. But when you compresses the gases, it is not isothermal. Okay, the temperature does not remain constant. Temperature increases. As we have already made the TS diagrams, in ideal case or isentropic compression, this is isentropic process. But you know that in case of isothermal compression, the work required for compression is minimum, right? Right. So if you want to minimize this compression work, then what you do is you just try to make this compression process more close to isothermal process, right? In our case, it is isentropic process, but we are trying to make this compression process more close to isothermal process. So what we can do is, instead of doing this whole compression in one stage, you can use multiple stages. You can use multiple stages. So when you use multiple stages, then what happens? Instead of compressing this whole thing in one go, first you compress it a little bit, then you cool it, okay, in an intercooler. Then again you compress it, okay, right? So 1, 2, 3, 4, okay. So this 2 to 3, it is intercooler, okay. So here we are using only one stages. Just imagine for a hypothetical case, if we were using a lot of stages, then how it will look like, okay. So it will look like something like this, okay. Compression, then intercooling, then compression, intercooling, compression, intercooling, compression, intercooling, okay, right? Then it will be more close to isothermal process, right? So this whole temperature, it looks like it is oscillating about some constant temperature, okay. So just to summarize, if you are using more than one compression stage, then you are basically moving close towards the isothermal compression, and the work required for compression in isothermal case is minimum. And doing the compression, high compression in single stage, that is difficult as well. Okay, that is difficult as well, because when you are compressing, then temperature is increasing, and the gases which have higher temperature, they have lower density. Okay, and compressing those gases is difficult. Okay, so a specific work that increases. So the purpose of using intercooling is to reduce the compression work. Now you can answer this question. Where is the intercooler typically installed? So this intercooler is installed between two compression stages. 1 to 4, this is sorry, 1 to 2, this is one compression, first compression, and 3 to 4, it is second compression. So intercooler is placed between two compression processes. So four options are there between the combustion chamber and turbine. This is not correct. Option B is between the compressors. Yes, this is correct. Okay. Now we can move to the next question. Question number 5. Question number 5 says, which of the following statement accurately describes the impact of incorporating a reheater in a gas turbine power plant? So in previous question, we have discussed heat exchanger, intercooler. Now this is reheater. So as the name suggests that we are reheating. So for reheating, what we will require is we will require another combustion chamber. Okay. And after combustion chamber, we will require another turbine. Okay. So instead of extracting the whole work output in one stage, we are using multiple stages to get the work output. Okay. This is first turbine, and 4 to 5. This is reheating. And there are two turbines, right? 3 to 4 and 5 to 6. This is only here we have only one stage of reheating, but you can have more than one stage of reheating as well. But if you can keep on increasing the stage of reheating, the additional specific work output, the increase in specific work output that you are getting, that increment will be keep on decreasing, but the complexity will keep on increasing. So at some point you will have to make a trade-off between these two parameters, right? So you cannot keep more than like 3 to 4, or you cannot keep infinite number of reheating stages, right? Somewhere you have to stop, right? But the purpose of using these reheating stages is to increase the specific work output, right? So four options are there. Use of reheater reduces the compressor work. This is not correct. We are not doing anything related to compressor, right? We are not disturbing compressor. Use of reheater reduces the heat supplied. This is also not correct. Use of reheater decreases the specific work output. This is not correct. We don't want to reduce the specific work output. We want to increase the specific work output. So only option D is correct, right? Now question number 6. It says for a given gas and maximum to minimum temperature ratio, the work ratio of the gas turbine plant then it is asking whether it reduces or increases with reducing the pressure ratio. So it is given that T max by T min, this is constant. Okay. And RP you are reducing. And work ratio. What is work ratio? Work ratio is net work output divided by turbine work output. So net work is not equal to turbine work output because some part of the work that is generated in the turbine is utilized to run the compressor. Okay. So work net is equal to turbine work minus compressor work. So you want to increase this work ratio. You want to increase this work ratio. Right? So it is saying that if you reduce the pressure ratio, then what will happen? It is saying that the ratio of maximum temperature to the minimum temperature, it is constant. Okay. So you have fixed T1 and T3. You have fixed these two temperature values. Now you are changing the pressure ratio. So this is one pressure ratio. Another can be like, let us make it in the another color. Another can be 2 dash, 3 dash, and 4 dash. Okay. So in this case, pressure at P2 prime, that is equal to P3 prime. This is more than pressure P2, and of course that is equal to P3. Okay. So you have reduced the pressure ratio. So you are going from dash case to the without dash case, right? So originally you were going like this, 1 to 2 dash, then 3 dash, then 4 dash. But now you have reduced the pressure ratio. So you will be going like 1 to 2, then 3 to 4. Okay. So what is happening here? The work ratio that will increase or decrease. Hello. Correct answer is it will increase. So here you can see that turbine work is increasing, but sorry, on reducing the pressure ratio. Here you can see on reducing the pressure ratio, turbine work is reducing, but compression work is also reduced. Okay. So this whole work ratio that will increase or decrease. Hello.
It's a little bit confusing.
Yes. Why? Because there are two things. One is compressor work and the turbine work. So if you try to write it, work ratio, it is net work, that is turbine work minus compressor work divided by turbine work. So it is 1 minus compression work divided by turbine work, right? So in this case, you can see the change in compression work is more as compared to change in turbine work. Okay. Am I right? Okay, we will come back to this point. Before that, we should discuss another important point that will help us to answer this question. We should understand what is our problem. Our problem is the change in these two values, right? Correct. If we make the HS diagram, it will look quite similar. 1 to 2, then 3 to 4. Okay. So we have to consider these two values, change in turbine work and change in compression work. So change in W and change in WC. Okay. So we will have two cases. Number one, if the change in compression work is more than change in turbine work, then what will happen when we are reducing the pressure ratio? So while reducing the pressure ratio, we have to check two things, change in turbine work and change in compression work. So if this WC it is reduced more, then what will happen? If it is reduced more, then what will happen? The work ratio will increase, right? Is this point clear? Let us say you are keeping the turbine work fixed, you are not changing that. Of course, it is changing, but for the time being, let us say turbine work is not changing, only WC is changing. So if you are reducing the WC, then this work ratio will increase, right?
Yes, sir.
Correct. So that is what I mean by this point. If the change in compression work is more than change in turbine work, both of these works are getting reduced. Turbine work is also reducing and the compressor work is also reducing. So if the reduction in compression work is more, then your work output, work ratio will increase. And the second case is that if the change in turbine work is more, then the work ratio will decrease, right? Now we have to see that which change is more, which change is more. So first of all, let us check the change in turbine work. So in turbine, initially it was how much? It was H3 dash minus H4 dash, right? And now it is H3 minus H4. And change in compressor work, it is initially it was how much? H2 prime minus H1, and now it is H2 minus H1, right? Right? Hello?
Okay, sir.
Now we have to see the slope of this HS curve. Slope of this HS curve. So we have to check dH by ds. So if this slope increases with temperature, okay, if this slope increases with temperature, then it will look like it is going more rapidly. It is increasing more rapidly when you are increasing the temperature, right? And if the slope reduces with the temperature, then it will mean that when you are increasing the temperature, then it is becoming more flat, right? So the thing is, you need to check the slope of these curve. So probably we should write the TDS relation. So what are the TDS relations? Okay. And since these lines are constant pressure line, so dP is 0. So dH by ds, it is temperature, right? Is this clear? Hello? So these curves will be moving,
Okay, sir.
should be something like this. this slope will be more and this slope will be little less. No. Now, if I try to make two diagrams, then at higher, and this will be little flat, something like this, right? And in between, it will be something like this, right? So here it is more slope, here it is something in between, and here it is little flat. Okay, now we got three curves. So first was 1 to 2. Then 2 dash. Okay. Then 3 dash 2. 4 dash. And then another case it was so from here now you can check. Now please pay attention. I am just zooming it in. Now check this part. Okay, this part, this change. Can you check this change and this change? This is delta H of compressor and this is delta H of turbine. So which is greater, delta H of turbine or delta H of compressor? Hello?
Delta H of compressor, sir.
Delta H of compressor. And how did we get this? From these concept, right? By making the correct sloped lines, right? Whenever we are making the TS diagram or HS diagram, we are roughly drawing some lines, but they are not parallelogram or they are not parallel, right? So the slope depends on the temperature and the slope is proportional to the temperature. At higher temperature, the slope is more, okay? And at lower temperature, slope is less. So less slope means it is something more flatter, right? More horizontal. And higher slope means it is more vertical. Okay. So using that concept, we draw these HS curves. Okay. And after drawing these curves, we just compared the change in compressor work input and the change in turbine work output. Right. So it is clearly here from this diagram, you can clearly see that change in compressor work is more and change in turbine work is less. So that is what we discussed just here. Okay. So if change in compression work is more than the change in turbine work, then work ratio will increase, right? Then work ratio, it will increase. And if the change in turbine work is more, then work ratio will decrease. So in this case, we are dealing with the first case, right? As it is clear from the diagram. Okay. So the correct option is increases. Is this clear?
Okay, sir.
Okay. So can we move to the next question? Maybe
Okay,
there
sir.
can be some better way to solve this question. There can be some another way in which you can reach these results in simpler way, but this is one of the way that I did. Okay, so this seems a little complicated, but anyways, so this is how you can proceed. Okay. So question 7. For question 7 to question number 11, some data is given. But these steps should be clear. Okay. And this is most important. This is most important. TDS relations. Okay. I forgot this TDS relation and I reached from this first step to here. Okay. So these small formulas from the thermodynamics, these should be, handy. So that in the case, if you forgot anything, you should be able to derive. Okay. This formula, right, you should remember, but if you forget, then you should be able to derive. Okay, so coming to the question number 7, but let us read the data, common data. A gas turbine cycle with a heat exchanger, okay, comprises of a compressor, fine, a turbine, each with a isentropic efficiency of 90% and 95%. So this means that compression and expansion in turbine, this is not isentropic. Okay, there are some irreversibilities. So the efficiencies are given, right? Isentropic efficiencies are given. If the compressor is not isentropic, if it is not ideal, then it will consume more work input. And if the turbine is not ideal, then it will produce less work. Okay, so this is what happens when it is not ideal case. The incoming air enters the compressor at an initial state of 1 bar, 310 Kelvin, with a mass flow rate of 1 kilogram per second. Okay. The pressure ratio for compressing the incoming air is 7. Okay. The pressure ratio for the incoming air is 7. The heat exchanger has an effectiveness of 80%. So this means that the gases which you are preheating, it is not heated up to the exit temperature of the turbine, exit temperature of the exhaust gases, right? It is not equal to the turbine exit temperature. The maximum temperature in the combustion chamber is 1200 Kelvin. It is given a specific heat at the constant pressure for air is this, and the specific heat ratio is 1.4. So gamma is given 1.4, and specific heat at constant pressure, so Cp, it is 1.005 kilojoule per kg Kelvin. Okay, so it is having a heat exchanger, isentropic efficiencies are given, and some other data is given. So now let us read the question 7. Actual temperature K at the exit of the compressor and turbine are respectively. So first of all, let's make the TS diagram. So if it was a ideal compressor, then the process would have been an isentropic compression, right? But since it is a not an ideal compressor, so it is something like this, right? So 1 to 2, right? This is our constant pressure line. These are not straight lines. Constant pressures lines are not a straight line, as we have already discussed. So at point 1, T1 was how much? 310 Kelvin and 1 bar. T1 is 310 Kelvin and it is 1 bar. The pressure ratio for the compressing the incoming air is 7. Compression ratio RP, it is 7, right? And we have to tell what? At the exit of compressor and the exit of turbine. So at the exit of compressor T2, and the exit of turbine. So where is the turbine? In the ideal case, it would have been something like this, but now it is something like this and this, right? So what will be T2? Hello? Hello?
Sir,
Hmm. How will you calculate T2? Let us say if it was an adiabatic, or sorry, isentropic process, then how will you calculate? Using the adiabatic relation, right?
yes, sir.
P1 V1 gamma is equal to P2 V2 gamma and the ideal gas equation, right?
Yes, sir.
So if it was an ideal case, then you could have calculated T2 is equal to, actually I should write T2S in the ideal case, then it would have been T1 into RP, that is pressure ratio, to the power gamma minus 1 by gamma, right?
Yes, sir.
Correct?
Yes, sir.
So then you could have got T2S is equal to T1. How much is T1? 310 Kelvin multiplied by RP. RP, how much RP? 7.
7.
7 to the power gamma. How much is the gamma? 1.5. 1.5, yeah, na?
Yes, sir.
Sorry, 1.4. Then it would have been 1.4 minus 1 by 1.4. Then how much is? Let me use the calculator. 7 to the power 0.4 divided by 1.4. So it comes out to be 540.5 Kelvin. So this is in the ideal case. But in the question, it is given that it is not ideal case because isentropic efficiency is given. So there are some irreversibilities, right? And isentropic efficiency of compressor isentropic efficiency of compressor that you can write as T2 S minus T1 divided by T2 minus T1, right? So this value will be less than 1, right? Because T2 S is smaller than T2, correct? This is how we define the isentropic efficiency. Is there any doubt in this step? Hello?
No, sir. No, sir.
Okay. And isentropic efficiency of compressor is given, it is 0.9, and T2S you have already got, so you can write 540.5 minus T1 was 310 divided by T2 minus कितना है 310. So you can write T2 is equal to 540.5 minus 310 divided by 0.9 plus 310, right? सही है. 540.5 minus 310 divided by 0.9 plus 310. So it is coming out to be 566. Okay. So this is actual temperature at the compressor exit. Okay. What else we need? We need temperature at the turbine output. Sorry, turbine exit. Hello.
Sir.
Yes. Hello. Any doubt?
No, sir.
Okay. So what else we need? We need temperature at turbine exit, and turbine exit it at 4. So we need T4. So we can proceed in the similar way, right? So if it was a isentropic process, then we could have used the adiabatic relation. But since it is not, then first we should find for S, that is for ideal case, and using the efficiency that is given, isentropic efficiency, we can find the T4. Okay, so first of all, let us find for S, right? Okay.
Okay, sir.
And what we have? Do we have T3? So yes, we have T3. It is given that the maximum temperature in the combustion chamber is 1200 Kelvin. And where is the maximum temperature? At T3, temperature is maximum. 1200 Kelvin is the maximum temperature. Okay. So T3 we have. We have T3. It is equal to 1200 Kelvin. Okay. So now we can find the T4. Right?
Yes, sir.
T4, sorry. T4S. So this will be equal to T3 divided by Rp to the power gamma minus 1 by gamma. Okay. And this is 1200 Kelvin divided by Rp7 to the power 1.4 minus 1 by 1.4. So we will get the TS. So this could be calculate. Seven to the power 0.4 divided by 1.4. So it is coming out to be 688.21 T4S. And then we'll use isentropic efficiency of turbine. It is how much? 95%, right? It is given 95%. So 0.95. So that will be equal to T3 minus T4 divided by T3 minus T4S. Okay, is this clear? So in this case, you can see T3, let us say it is constant, and 4S, it is T4S, it is less than T4. So this whole efficiency will be less than 100%. T3 is 1200 Kelvin minus T4 we need to find, and T4 as we have got, it is 688.21 Kelvin. Okay. So you can write 1200 minus 688.21 Kelvin. I'm not writing the unit. Is equal to 1200 by T4 divided by 0.9.95. Okay. So T4 will be equal to 0.95 times 1200 0.95 minus 1200 plus 688.21. Is this correct? Hello?
Okay, sir.
So can you please calculate this value? 0.95 times 1200 divided by 0.95 minus 1200 plus 688.21. So it is coming out to be 713.79. So T4 is equal to 713.79 Kelvin. Okay, or 713.8 Kelvin. Okay. So we got the T4. And yes, this is what we were supposed to find. We were asked to find the temperature, actual temperature at the exit of compressor and exit of turbine. So at the exit of compressor, it is T2, this is 566, and at the exit of compressor, it is 713. So 566 and 500, sorry, 7, it is approximately equal to 714 Kelvin, right? So option C is correct option, right?
Okay, sir.
Okay.
Okay, sir.
So moving to question number 8. Power consumed by the compressor. So it is easy. What it will be? Power consumed by compressor. Hello?
Sir,
Mhm. Yes. What will be the power consumed by compressor? Sorry. What it should be? We know the temperature at the inlet of compressor and the outlet of compressor. Hello?
sir,
Mhm. It should be simply H2 minus H1, right?
yes, sir.
This is TS diagram. This is 1, 2, 3, 4. This should be simply H2 minus H1. And you can write Cp, T2 minus T1, right? This is small w, okay? So specific work. Cp, it is given 1.005 kilojoule per kg Kelvin, right? Temperatures, we have already got T2. How much was T2? 566. 566 minus 310 Kelvin. So you can easily calculate this value. 1.005 times 566 minus 310. So it is 257.28 kilojoule per kg. This is specific work input to the compressor. And what will be the power input to the compressor? It will be, we just need to multiply by the mass flow rate of the air, right? Times specific work input. And what is the mass flow rate of air? With a mass flow rate of 1 kilogram per second. Okay, 1 kilogram per second, it is given. It is given. So just need to multiply it by 1 kilogram by 1 kilogram per second. 257.28 kilojoule per kg times 1 kilogram per second. So you'll get 257.28 kilojoule per second. So it is basically 257.28 kilowatt, right? 257.28 kilowatt. So in kilowatt it is asking, right? So 257 kilowatt. The correct option should be option D, right? So this is very simple. Whether you need to find the work input to the compressor, it will be H2 minus H1. Heat supplied in the combustion chamber, it will be H3 minus H2. Work output of the turbine, it will be H3 minus H4, right? And
Okay,
if
sir.
you know the temperature, then you can easily find the H. Okay. Okay. So now coming to the question number 9. Question number 9, it is saying heat transfer kilojoule per kg to the working air in the heat exchanger. So first of all, again, let us make the TS diagram. We did not consider heat exchanger till now, but now we need to consider it. So first of all, 1 to 2s, but actually we have 1 to 2. Then 2 to 3 heat addition, and then 3 to 4s it would have been, but it is 3 to 4. And then there is heat exchanger. So heat exchanger means instead of adding all the heat in 2 to 3, first of all we are preheating this air. Okay, so 2 to let us say 5, 2 to 5, it is heat exchanger. And थोड़ा सा इसको नीचे बनाना चाहिए. Okay, so again T5 will be still less than T4. Okay, hello, because heat exchanger,
Okay.
yes, because the heat exchanger effectiveness of heat exchanger, it is not 100%. Effectiveness of heat exchanger, it is 80%. Okay, so what I mean by effectiveness is how much temperature is increased in the actual case. So how much temperature is increased in the actual case? In our case, in the heat exchanger, it is T5 minus T2. This is the actual increase in temperature, correct? Are you getting? Here it is heat added in the heat exchanger, and 5 to 3 it is heat addition in combustion chamber. Okay, so in the actual case, we the increase in temperature is from 2 to 5. But if this heat exchanger had the 100% effectiveness, then we could have reached to the maximum point up to 0.4, right? If the heat exchanger has 100% effectiveness, then we could have increased the temperature up to T4, right? Hello,
Okay, sir. Okay,
is this
sir.
clear? Is this clear?
Yes, sir.
T, T4 is the temperature of exhaust gases which are coming out from the turbine. If the heat exchanger has 100% effectiveness, then this is the maximum temperature that we could have reached. But actually, we are reaching only up to 0.5. So T5 minus T2 is the actual temperature rise, and maximum temperature rise could have been T4 minus T2. Correct?
Yes, sir.
So T2 we have already calculated in previous question. T4 also we calculated. Now we can calculate T5 since we have the value of effectiveness. Effectiveness it is given 80%, so 0.80. It will be equal to T5 minus T2 divided by T4 minus T2. So it will be 0.8 is equal to T5 minus T2 was 566 divided by T4. How much is T4? T4 is 714. 714 minus 566. So from here you can calculate T5, right? So T5 will be 0.8 times 714 minus 566 plus 566, correct? So 0.8 times 714 minus 566 and then plus 566. So it is 684.4. So T5 is equal to 684.4 Kelvin. Okay. So the heat transfer to the working air in the heat exchanger will be how much? Hello?
Sir,
Huh? Hello? How much it should be? How much heat you are adding in the heat exchanger? How much heat you are adding to the working air in the heat exchanger? Can you see?
T5 minus T2, sir.
T5 minus T2 multiplied by Cp, right?
Sir.
So heat added to the working air in heat exchanger, it will be Cp times T5 minus T2. T5 is 684.4. T2 was 566. Kelvin and Cp was 1.005. So this value will be in kilojoule per kg, right? So if you calculate this value, it will come out to be 1.005 times 684, sorry, 684.4 minus 566. So it is coming out to be 118.992. So it is approximately 119 kilojoule per kg. Okay, is this clear?
Yes, sir.
119. So four options: 101, 131, 119. So option C is correct. Okay, 119 is the correct option. Okay, is this clear?
Yes, sir.
So we move to question number 10. Yes. Back work ratio. So you know the work ratio, but it is back work ratio. You know what is back work ratio?
Yes, sir. Work on turbine divided by work on compressor.
Yeah, it is just opposite of whatever you are saying. Okay, so it is work input to the compressor divided by work input to the turbine. This is work ratio, back work ratio. Sorry, back work ratio. Okay.
Yes, sir.
So how to calculate this? This is very simple. We just need to WC we already have, right? Compressor work input. In the first question, I think we calculated power consumed by compressor 257, and work output of the turbine also we can get, right? Have we calculated the work output of the turbine? Okay, we have not, but work output of the turbine will be how much? H3 minus, sorry, H3 minus H4, right? It will be H3 minus H4, right? So Cp T3 minus T4. So 1.005 times T3 is 1200 Kelvin. Maximum temperature was given in the question. Minus T4 we calculated somewhere. T4 कितना है? 7 714 Kelvin. So this will be kilojoule per kg, and since it is 1 kilogram per second, so okay. One 1.005 times 1200 minus 714. So work output from the turbine, it is 488.43 kilojoule per kg per second, of course. Okay. So back work ratio will be turbine compressor work. How much? Compressor work was 257 divided by 488.43. 257 divided by 488.43. So it comes out to be 0.526. Okay. So you want more back work ratio or less back work ratio? Hello? Less back work ratio, because you don't want more work to be consumed by compressor. But anyways, in this question, correct answer is 0.527 or 0.53. And if we say work ratio, it is net work divided by work output, turbine work. And so we want more work ratio, but if it is back work ratio, then we want less work ratio. Okay. So I hope this is clear. If there is no doubt, then we should move to the question number 11.
Okay, sir.
It is saying thermal efficiency of the plant. So thermal efficiency you can easily calculate. Thermal efficiency. What is thermal efficiency? It is net work output, right, divided by total heat input, right? So net work output we just calculated, it was 488. No, this is not net work output. This is turbine work output. So 488.43 minus 257. Okay, this is the net work output divided by total heat input. How much is the total heat input? Did we calculated heat input? Okay, we did not calculate it, so let us calculate it. So what will be net heat input? Sorry, heat input. So heat is being added from 5 to 3, right? Because 2 to 5 it was preheating in the heat exchanger. Now 5 to 3 it is heat input by fuel, right, in the combustion chamber. So heat input will be H3 minus H5. So it will be H3 minus H5. It will be Cp T3 minus T5. 1.005 10.200 and T5 was 684.4. 684.4 kilojoule per second. One 1.005 times 1200 minus 684.4. मल्टीप्लाई है भाई, 1200 minus 684.4, 518.178 kilowatt, and work output is, net work output, it is this much. So thermal efficiency will be 488. This is turbine work output minus 257. This is compressor work input divided by heat input. This is 518.18. So it is approximately 0.446. Okay. So it is 44.6%. Okay. So the closest value is 45. Okay. So option B should be the correct option. Okay. Fine.
Okay, sir.
And we have one more question. Sorry, two more questions. Yes. Maybe we can solve. I think we can solve both. So question number 12 says air enters the compressor of a gas turbine plant operating on Breton cycle at 1 bar 27 degrees Celsius. The pressure ratio in the cycle is 6 if turbine work output is equal to 2.5 times of compressor work input, right? Where WT and WC. Okay, so this should be subscript WT, WC, WT, WC. WT and WC are the turbine and compressor work respectively. We have to find the maximum temperature and the cycle efficiency. So it is quite easy, right? So should we solve it, or you can solve?
Okay, sir.
Huh? Hello?
Sir,
Should I solve it, or you can solve it by yourself? It is very easy. Okay, it is simple. Breakdown cycle.
okay, sir. We can solve, sir.
Okay, maybe I can tell you the answers. Okay, then you can just cross check. So answers that I have, uh, the maximum temperature. So just you first of all you should make the TS diagram. Okay, so 1 to 2 it is isentropic compressor, then 2 to 3 it is heat addition, then 3 to 4 it is turbine. Okay, simple Breton cycle. Okay, then you have to find the temperature at point 3. So you have to find temperature T3, and you have to find the cycle efficiency. You know the cycle efficiency, right? Pressure ratio is given, so I think that is enough to find the cycle efficiency, right? Pressure ratio is given, right? Or if you want to use the formula of cycle efficiency, that is net work output. So net work output will be uh, turbine work. So turbine work will be T3 minus T4 into Cp, and minus compressor work, it will be Cp T2 minus T1 divided by heat input. This will be Cp T3 minus T2. And these values of temperatures you can easily get, right, using the adiabatic relations. Okay, and so T3 you will find as T3 is equal to, answer I have, it is given 1251, and neta I have it is 40%. So you can just calculate. If you find any difficulty or you are getting some other values, then just let me know. We can solve it in the next session. So it is easy, right? I should not solve this. Okay. And
Okay, sir.
last question number 13 says a closed cycle ideal gas. So again, it is ideal gas power plant. So no irreversibilities. Operates between temperature limits of 800 degrees Celsius and 30 degrees Celsius. So this is the maximum and minimum temperature. Okay. Produces a power of 100 kilowatt. Okay. So this is net power output. Okay. Turbine work output minus compressor work input. The plant is designed such that there is no need for a regenerator. Okay, so there is no heat exchanger. Regenerator is basically a heat exchanger. Okay, so not confused. A fuel of calorific value of 45,000 kilogram per kg is used. Okay, fine. Calculate the mass flow rate of air through the plant and the rate of fuel consumption. So this is also easy, right? So first of all, you should make the TS diagram. A simple cycle, 1 to that is compressor, 2 to 3 it is heat addition, 3 to 4 it is turbine. Okay, so temperature at point 1 is given. T1 it is 30 degrees Celsius. First of all, you should convert these values into Kelvin. Okay, so T1 will be 303 Kelvin, and temperature at point 3, T3 will be, it is 800 degrees Celsius. So if you convert this into Kelvin, it will be how much? 1073 Kelvin. Okay, fine. And it is given that it is producing 100 kilowatt power. What else we need? We need some other value, right? Because it seems okay. It is given that there is no need for regenerator. So this means that T4 should be equal to T2. Okay,
Okay,
right?
sir.
Because we are not using any regenerator. So it means the turbine is expanding the gas up to T2 in such a way that exhaust gas turbine is equal to the temperature of gases which are coming out from the compressor. Okay, so it should be something like this. Okay, okay, so T4 is equal to T2. So I think now it is fine. Okay,
Okay, sir.
and P2 is equal to P3, P4 is equal to P1. So now how will you proceed? Hello?
Sir.
Yes. You can write P2 by P1 is equal to P3 by P4, right? And P2 by P1 in terms of temperature, if you write, it will be T2 by T1 to the power gamma minus 1 by gamma. Sorry, opposite. Gamma by gamma minus 1, right?
Okay, sir.
And P3 by P4, it will be T3 by T4, and same thing, gamma, gamma minus 1. And these two things are equal. This is equal to this thing. So from here you will get T2 by T1 is equal to, sorry, you will get T3 by T4. Okay, and T4 is equal to T2. T4 is equal to T2, so you can write T2 by T1 is equal to T3 by T2. So you can write T2 square is equal to T1 T3. Okay. And T1 and T3, it is given in the question. 30 डिग्री सेल्सियस, ये केल्विन में होगा तो 303 केल्विन, सॉरी 303 Kelvin. So T2, sorry, T1 we have, T3 we have, and T2 is root of T1, T3. So you will get T2. Okay. So now you have T1, you have T2, you have T3, you can, and you also have T4, that is equal to T4. T2 is equal to T4. So now you have all the temperature values, right? Hello? You have the temperature
Yes,
values.
sir.
Okay. So the specific, so what we need, calculate the mass flow rate of the air through the power plant. Okay. So the net work output per unit mass of air. So this will be equal to work output of turbine. So that will be equal to, just write the real values. So it will be equal to Cp, and of course there will be mass flow rate, Cp times T3 minus T4 minus compressor. This will be T2 minus T1. Okay. This is network output, and this is given to be how much? It is given 100 kilowatt. It is given 100 kilowatt. This is given 100 kilowatt. So in this equation, you know the Cp, right? You know the Cp, you know the T3, you know the T4, you know the Cp, you know T2, you know T1. So from here you can calculate M, right? Okay.
Yes, sir.
Mass flow rate.
Yes.
All the values you have already calculated. Okay. So mass flow rate you can calculate. So it is coming out to be, what answers I have, it is given 4.74 10 to the power minus 3 kilogram per second. Okay. So just do this calculation, and if you are getting something else, then we can solve it in the next session. Okay. So mass flow rate of air you have. Okay. And calorific value of the fuel is given. Calorific value of fuel is given. So basically we need to find heat input Q in. So this will be mass flow rate of air times Cp T3 minus T2. So this is heat input, and this should be equal to mass flow rate of fuel times calorific value of fuel. Okay. So sorry, and this would be equal to mass flow rate of fuel times calorific value of the fuel. Okay. So mass flow rate of fuel you can calculate as mass of air that you will get from this first part of the question, Cp T3 minus T2 divided by calorific value. Okay. Is this clear? So mass flow rate that I have in the question. Okay, so actually this is not the correct answer. This is mass flow rate of the fuel. So this was 4.74 into 10 to the power minus 3 kilogram per second. Okay, so 4.74 gram per second as mass flow rate of air. It is coming out to be 0.414 kilogram per second. Okay, so this is
Okay,
quite
sir.
easy question. Okay, so is there any doubt in any question or any other doubt that we should discuss here?
No, sir.
Okay, so thank you. If there any doubt, then you can let me know. We can discuss in the next session. Okay, thank you for joining. We will meet in the next session on next Tuesday. Okay,
Thank you, sir.
thank you.
Good night, sir.
Good night.